Hello, my name is Nick van Helleputte and I'm working at IMIC in Belgium. My current research interests include low-power analog circuit design for biomedical applications. I have presented paper 6.5 entitled 160 microamp biopotential acquisition ASIC with a fully integrated instrumentation amplifier and motion artifact suppression. The motivation for this research was to develop systems that can enable home care and remote healthcare solutions. An important aspect or problem that you need to address for those kind of solutions is the fact that people are going to be wearing devices while they're walking around. And that can lead to significant artifacts as shown here that will potentially disrupt your readout. So these systems that we're going to develop need to address those artifacts. I'm presenting here a paper, a chip actually that provides real-time motion artifact suppression. In my demo, I will be using this hardware here. On the small PCB, we have the chip that I'm presenting mounted, and you can see the area which corresponds to this sticker here. You have a larger PCB which contains an external microcontroller to interface with the chip, an FTDI chip to interface with the computer. The whole setup is powered by the 5-volt USB, so there's some power control as well. All of the core functionality though is provided by the chip that I'm presenting here. For this demo, our chip has 3 readout channels, and I have shorted the inputs of 2 channels to the same electrodes which I have attached across my chest at these locations. So we have 2 channels that are measuring the exact same signals. On one channel I have enabled the motion artifact suppression, and on the other I have disabled it. So you can clearly see the benefit of our proposed system. If I move a little bit to the side, you can see the real-time readout of the system that I'm wearing here right now. On the top side you can see the ECG readouts, the 3 channels. The first 2 channels are indeed measuring the same signal. The third channel is measuring a completely unrelated ECG. I've attached the electrodes across my chest like this. Now I am standing still and there is no artifacts present. So the ECG readout is looking quite nicely. There's no, the baseline is very flat. You can also see that the bottom curves, which show the electrode tissue impedance, are very flat. So we are measuring ECG concurrently with electrode tissue impedance. And this is actually the key to estimate the motion artifact, because any variation in the impedance correlates with the artifacts that are present in the ECG readout. So we will use the bottom curves to estimate the artifacts that's present. So I will now introduce some artifacts by pressing, for example, on one of the electrodes. So I'm just pressing on one of the electrodes, and we will see that in the ECG readout there's a significant baseline variation. Especially the black curve, which has the motion artifact suppression disabled, is going up and down a lot. Now, looking at the impedance measurements, you can see that there is indeed a variation which is very similar to the artifacts. We're using those impedance measurements to estimate the artifacts that are present. Currently the estimation is running on the external microcontroller. We're feeding it back to the chip itself, and we're suppressing the artifact in the analog domain on the channel where the motion artifact suppression is enabled. And you can see that the red curve has much less baseline variation than the black curve. Currently, the limiting factor of our solution is the actual estimation of the motion artifact. Obviously, the better you can estimate the artifact, the better you'll be able to suppress it. The algorithm that we're using is a standard textbook LMS algorithm, and we are actually researching more advanced algorithms as we speak. So